So my name's Jack Beuth. I'm a professor in mechanical engineering, but I'm also director of our next manufacturing center. That is our additive manufacturing center at Carnegie Mellon. I've been in the area of additive manufacturing for about 20 years. So I don't go all the way back 30 years when additive first started, but I go back quite a ways. And in our center, we're covering research. Our research covers quite a bit. As you've seen, there's a very wide landscape of what we really call additive manufacturing. A lot of applications, a lot of different processes. And we cover many of them. Micro-scale polymer type additive manufacturing, macro-scale polymer additive manufacturing. Adam Feinberg, after my talk, will be talking about bioprinting. That's another form of additive manufacturing. But then what I'm going to talk about today is focus a little bit in on the metals processes. And you may not be, completely up on, what's really exists in the metal sphere of additive manufacturing. Yeah, so first slide. I just really have a few slides here. First one relates to really what is the current state of the art with respect to the direct metal processes. And it's interesting. Most of you are probably well aware of the maker movement and the maker machines, which it's really democratized the printing of polymer type parts. And that really started about 6 years ago. But almost at the same time, but independent of that, metal 3D printing became possible. And in fact, there are two types of processes that are fully automated, where you can take a CAD model of a part, that's a computer-aided design model of a part, and turn that into a 3D shape. There are two processes that can do that automatically. They're laser and electron beam. They're both powder bed processes. And I'll show you a video of a laser process on the next slide. And we've got a table in the back of the room here. There's a video playing continuously for an electron beam powder bed process. And in fact, that one's actually really neat. It almost looks like the replicator on Star Trek, next generation Star Trek. So the reality is right now, in fact, you could have inferred this from the talks earlier on, the reality is you can pretty much print almost any 3D shape directly out of metals. And it's not just any metals, but engineering alloys, titanium alloys, nickel superalloys, steels, aluminums. You can print pretty much any 3D shape. That technology exists. Now, there are some limitations. In fact, I've got a couple of them up there on the slide, if you can see them, and those aren't all of them. But one of the big limitations is the processes tend to be a little slow, in that if you're printing out a part, it can take anywhere from 4 to 8 to 24 hours to print a single part out. And so although GE is sort of breaking the barrier here in producing actually fairly large numbers of parts with these processes, it is a challenge to do mass production with these processes. And another issue is that these are powder bed processes. And there's really currently there are a limited number of types of powders that you can use in the machines. And in fact, you're supposed to use powders that you buy from the machine manufacturers, although many people that have the machines go around that to some extent. But it is true there's a fairly narrow range of powders you can use in the machines. And finally, on this slide, the idea is that really the current processes as they exist were really, in fact, they were developed over about a decade. They were really developed to allow you to print a shape out of metals. But if you're really going to use this as a manufacturing process, there's much, much more you need to do than just print a shape. You want to have the material properties, the mechanical properties of the part to be the properties that you want to have. A key one would be strength. Another one would be resistance to cyclic loading. If you load something on and off thousands and even millions of times, you want to have the life of that component to be sufficient. There's surface finish issues. There are issues related to the resolution of the process in being able to make a certain shape. So those other process outcomes you also want to be able to manipulate, and you would like to be able to manipulate that by changing the process variables, actually changing the way the machines run. And at this time right now, that's an evolving area. Let's see, I've got, just before I switch off this slide, I've got a couple of pictures of parts. In fact, I invite everybody to come back and take a look at some of the parts at the back of our table. The one at the very top end there is a sort of model compressor blade. And in fact, we got that model from GE as part of an America Makes project. And there are a couple of those compressor blades on the back table. If you can see it there at the bottom, that's actually a meshed sphere. And we make those mesh spheres as part of our undergraduate course in additive manufacturing. And I'll pass a couple spheres around the room. You want to catch it? Do you want to take one there, maybe one for that side of the room? And it was mentioned earlier that added complexity does not incur added cost. And that mesh sphere is an example where you can have very, very complex geometries. And in fact, those types of meshes can be automatically chosen. You can take a part and you can choose to mesh it out three-dimensionally very easily in the planning software for these machines. And in fact, I would say 5 years down the road, to the extent that direct metal additive manufacturing is accepted, you may start to see very few solid parts. Parts will be more like a shell, and then you would have a three-dimensional cellular mesh on the inside. Can you play the movie? This gives you a sense, it was already described sort of how the laser processes work. This is a view of a process. We just spread powder over top, and you can see the laser itself is moving across the part. And this is on an EOS machine, electro-optical systems. They fill in the two-dimensional shape in stripes. And although it looks like there's just a bar of energy moving along each stripe, that's really a laser that's moving back and forth across the width of each stripe as it moves along the length. Okay, and again, you can see a similar process in the back of the room for the electron beam processes. So, where are these metals processes going? We like to, we're in the research game, and so we like to look at where the processes are going to be in the next 5 to 10 years, and then how our research can impact that. And the first thing that we've seen, in fact, this is happening now already. We get about 2 or 3 visitors to come to our lab every week, industrial visitors, and it's gone from being mostly aerospace companies, aerospace-related companies, some medical implant companies, to now really every company that makes metal parts is very much interested in additive manufacturing. And they may not be adopting it immediately, but they're very concerned and they want as much knowledge as they can get. And within 5 years, I can see it spreading across really the entire metals manufacturing sphere. Also, the processes themselves are going to change significantly. Within 5 years, we see that you will be able to manipulate the process significantly. In fact, you'll manipulate it as you're trying to design a part. There's a capability of changing the microstructure or the properties spatially within a part. So you'll have different properties at different locations in the part. We're working on that right now, and I think we actually are about to make a few breakthroughs in that area. The whole issue of limited types of powders, that's going to go away. There can be a wide range of powders that can be used in these processes. Currently, the processes can have some amount of porosity in them, the actual parts that you make. There are ways of taking that out, and that will disappear. And last thing is the metals processes currently, it's amazing what you can make with the processes as they exist, but they are not very well sensed processes, meaning you're not monitoring what's going on as the part's being built up very well. That's going to change. You're going to be monitoring them quite a bit. And my next slide makes the statement here that, looking ahead 5 years, really, whether you're talking about a country, nations, whether you're talking about a region within a country like southwestern Pennsylvania, that's what we talk about because we're in Pittsburgh, Pennsylvania, whether it's companies, industries, individuals, the ones that really recognize where additive is heading, and they get to that point as the processes are changing, they will clearly outcompete the people or the industries or the countries that don't do this. And this is one of the things I keep telling my graduate students as they're working on their projects. The clock is ticking, or at least the race has already started. And it's a case where really time is of the essence to keep up with what's going on here. And last slide. What can you do recognizing that this is happening? I've got a number of bullets here. First thing I can see, promoting this kind of highly collaborative university industry type research to the extent that it can be done. Now, America Makes has really made substantial progress in this area on projects where it's really a tech transfer project. That means it's a technology that's already there in the university, for instance, and it's being transferred directly to industry. But there's also an opportunity for much more fundamental research projects, probably carried out by groups that are more regional. America Makes is trying to cover the entire country all at once. When you look at agencies, government agencies, two key ones are NIST and FAA. Each of them, NIST is involved with standards, FAA is involved with certification. Each of these industries really has to make sure they get up to speed to where the technology is now, and they keep up with it as it is changing. And in fact, particularly the FAA, we talked to them quite a bit, and they're very concerned that the aerospace companies are starting to bring them parts, or they're telling them that parts are coming, and they're going to want to have those parts certified by the FAA, and that means the FAA has to know very well exactly what goes into making those parts. Universities, we're starting to do this, but I think at least all the top universities have to do this. Start integrating metals, additive manufacturing into their undergraduate curriculum, and it's possible to do that. Again, we're working toward it, but again, time is of the essence. And Ed mentioned workforce training. When we talk to companies and individuals involved in additive manufacturing, there is a real hunger for anyone that has experience or knowledge with respect to additive. And so I actually consider this a bottleneck, that there are a lot of companies that would like to move ahead with additive, but they just can't find the people, whether it's technicians or students with an undergraduate degree, a BS degree, PhD level students. They can't find the personnel that really know enough about additive to take them to the next level. And the last thing is machines. There's a bottleneck where there really aren't that many of the direct metal machines in the country right now. And they're somewhat isolated at certain universities. Carnegie Mellon is one of them. And to me, I think we could really jump ahead if we really located direct metal machines strategically throughout the country and made them available to collections of universities and also to companies. That's an easy way to get a jump start on everybody else. And that concludes my talk. Thank you.